Imagine wearing a device that not only helps you hear the world again, but also listens back to your brain, checking in real time how well you are hearing. That's exactly what researchers have just achieved with cochlear implants. Instead of needing wires and bulky EEG caps to record brain activity, the implant itself can capture the brain's response to sound. This idea of a smart implant that both stimulates and records could completely change how we monitor and fine tune hearing restoration. So let's begin our lecture. People who lose most or all of their hearing often receive a cochlear implant. A cochlear implant is a small electronic device that bypasses damaged parts of the ear. It directly stimulates the auditory nerve with electrical signals, which the brain interprets as sound. Cochlear implants are considered one of the most successful treatments in modern medicine for restoring access to sound. But not everyone benefits equally. Some people hear very well with the implant, while others struggle. Doctors and audiologists need tools to check how well the brain is actually processing the sound from the implant. This helps them adjust or program the device for the best results. Currently, one way to do this is by recording cortical auditory evoked potentials CAEPs. CAEPs are brain signals that show up when the brain responds to sound. These are detected as small voltage changes in the brain's outer layer, the cortex, using electroencephalography EEG electrodes placed on the scalp. By looking at the shape of these waveforms, for example, peaks named P1, N1, P2, scientists can see how well the brain is hearing. P1, N1, P2 peaks are distinct waves in the brain response that happen at different times after a sound. They are like markers that show different stages of sound processing in the brain. The problem, though, is using EEG is time consuming, expensive, and not practical for routine clinic visits. The goal was to see if a cochlear implant could deliver the electrical stimulation as usual. Also, record the brain's response using its own electrodes. If this works, it means the implant could act as both a speaker and a microphone for the brain, giving real time feedback without the need for extra equipment. Methodology. Selected participants were adults who already had cochlear implant. To provide stimulation, the implant sent out special test pulses designed to activate the auditory nerve. Normally, brain responses are picked up by sticky electrodes on the scalp EEG. Here, researchers tried recording directly through the intracochlear electrodes, the thin wires already placed inside the cochlea as part of the implant. To compare, for each participant, responses were recorded in both ways, scalp EEG and implant recording. This allowed the researchers to compare whether the implant could capture the same patterns. What they found was that the direct recording worked. The implant successfully recorded brain responses to sound. These signals are called electrically evoked CAEPs, and they looked very similar to the standard EEG responses. When comparing the two methods, the same peaks P1, N1, P2 appeared in both recordings. The timing and size of the signals were closely matched. This shows the implant recordings are reliable and not just noise. Because the implant itself can do the recording, Clinics wouldn't need bulky EEG systems. Audiologists could quickly check whether the brain is responding well to sounds delivered by the cochlear implant. This makes it possible to personalize cochlear implant programming in a simple and direct way. The significance is that this method could make brain based hearing checks much easier. It could be used during routine appointments instead of requiring specialized EEG labs. It might allow real time adjustments of the implant while directly monitoring how the brain is responding. That's it for the lecture series of Smart Implantable in Biomedical 5.0. Until next time, take care of yourself.